All right, so recording is on. Let me bring up my sheet here. Okay, are you guys able to see my whiteboard?
Yes.
All good? Can someone confirm?
Yes, we can see.
Okay, cool. All right. So last week we did a few miscellaneous topics. I don't know why this happens always. Rectangle, spline. Sorry, guys. Okay, I think it should be good. Okay, cool. So let's start with quadratics today. Recording is on, I hope, right? Let me just confirm. Yeah, recording is on. Okay, so we'll start with quadratics and polynomials. Okay, again, so all of this should be basic information you guys will know. So first of all, when I have ax square plus bx plus c, okay, so that's an expression. So this is an expression. Okay, so just so that you know the difference between expression, function, and an equation, right? So this is an expression. When I set y equal to ax square plus bx plus c, you're essentially saying y is equal to some expression. Y is an expression in terms of x, right? In terms of x. And therefore, it's a function. So y is a function of x. Y is a function of x. I mean, no one is going to ask you theory and all, but just so that you're very clear. And then, of course, if I set ax square plus bx plus c to be some value, it does not have to be 0. If I set it equal to some value t and ask the question, when does this happen, right? When does this happen, right? As in, for what values of x does this happen? Then there's an equation. So this is an equation. So in other words, you can just say y equal to ax square plus bx plus c, and you can ask the question, when is y equal to t? Okay, that's also an equation, right? Y is ax square plus bx plus c, and you set it equal to d and ask the question, for what value of x does this hold true? So three things, right? Expression, function, equation. Okay, so expression, what can you do with the expression? You can only factorize an expression. I can write it as a times x minus something times x minus something. What does factorization mean? Factorization means splitting into multiplicative units, right? So if I have a into x minus alpha times x minus beta, right? That's factorization. Why? Because I have multiplicative units, and then I'm bringing them together through the multiplication sign. So a, in a way, there are three multiplicative units here. A is separately a unit, x minus alpha is another unit, x minus beta is another unit. Okay, and same thing for an expression also, you can just say this, right? And for an equation, again, this helps because it helps me solve the equation. If I have this, and typically you can always move the d to this side and effectively say it's ax square plus bx plus another c. It could be c prime or something, but effectively you can say it is equal to the right hand side is 0. Doesn't have to be 0. You can always move around things and make it equal to 0. So effectively I'm looking at this guy, and you're asking the question, when is it equal to 0? And it's convenient to set the right hand side to be equal to 0 only because if the right hand side is 0, then it means surely one of these is 0, right? And that helps solving. That's why we always set it equal to 0 and solve, right? So sometimes it's very tempting to solve without having the right hand side as 0. That can, in some situations it might work out, but in many situations you might miss out some solutions. We'll see examples like this, right? So always when trying to solve something, set the right hand side to equal to 0 and let the left-hand side speak for itself whenever it happens, right? So in this case, obviously, there are two solutions. The reason the factorization helps is now I can say this right-hand side is 0 whenever A is 0, which typically is not the case, because if A were 0, we are not even talking quadratic, we are talking linear here. So it's just bx plus c. Or when x minus alpha is 0, which happens when x equal to alpha, or when x minus beta is 0, when x is equal to beta, right? So therefore, x equal to alpha and x equal to beta become the roots or solutions or zeros. All of these are synonymous terms, right, of the equation, right? Sometimes people say, what are the roots of this function, right? So technically it's wrong. A function does not have roots. But what they mean is, if you set it equal to 0, what are the resulting roots? That's what it means. So when you see an exam, when you see a question like that, that's what it means. But technically, a function does not have roots or zeros or solutions, right? Only an equation has. Okay, now you can write the quadratic in multiple ways, right? So if I have ax square plus bx plus c, that's the Cartesian way. Of course, this is the Cartesian way of writing, or the normal form. I can take a outside, and when I write it like this, okay, so this is in a form like sum of roots and product of roots. So I'll come to that in just a second. So sum and product. Say sum and product. And product form. So why do I say it's sum and product form? If I write it as a times the third form, then this is the factorized form, x minus alpha times x minus beta. This is the factorized form. Each one has its own benefit. The factorized form helps us immediately identify what the solution is. If you set it equal to 0, then the roots automatically come out as alpha and beta. And then I'll just cover the last form and then come to the second one, right? You have a into x minus h whole square plus k. This is the vertex form. Okay, so now if alpha and beta are the roots of the equation, I mean, it's set it equal to 0, that means I can expand this. If I expand this, what do I get? I get a times x square minus alpha x minus beta x. Therefore, it becomes alpha plus beta times x plus alpha beta equal to 0. Therefore, the sum and the product are this, right? Alpha plus beta is the sum. So I can do some association here and say this is effectively a times x square minus b by a times x plus c by a equal to 0. And therefore, the sum of roots is minus b by a by comparison, and the product of roots is c by a by comparison, right? And that's the exact same thing that you get when you actually solve the quadratic equation, right? So how do we quickly solve the quadratic equation? Again, no one is going to ask you to solve, but it's good to know, right, where it comes from. So if you set it equal to 0, the first thing you would do is get rid of the a, as in make it like this, and not get rid of the a, as in make the x square coefficient a, x square coefficient 1. It's always convenient to have that. And then the normal completing the square. So you'll make it as x square. Suppose you want this to behave like p plus q whole square, then x square is p square. That's how I'm reading. 2 times x times 2 times p times q. You pause for a second and ask what that q should be such that it matches with b by a x. So you can discover it's b by 2a. Okay, so I have p square plus 2pq. So you add q square to complete the square. Okay, and that's not going to come for free. So you're going to add b by 2a whole square on the right-hand side as well. And the c by a just continues along. And now this collection now becomes a square, right? It's p plus q whole square. So in our thing, p is x and q is 2a, b by 2a. So you have x plus b by 2a, the whole square equal to, let's move the c by a to the other side. So it's b square by 4a square minus c by a. Okay, so you can already see it's taking shape. And then I can bring common denominator as b square minus 4ac whole upon 4a square. Therefore, when I take a square root, it becomes x plus b by 2a equal to plus or minus square root of b square minus 4ac. Okay, and we talked about it in the past, right? So square root is always the positive square root upon, technically I should say plus or minus 2a, right? Because the square root of 4a square need not be 2a, right? If a is negative, then it's minus 2a. So I don't know if A is positive or negative. So technically, I should give the same treatment to the denominator. I should put plus or minus. But effectively, rather than have plus or minus both in the numerator and denominator, I can just have whatever it is, it's finally going to be 1 plus or 1 minus for this, right? So it's plus or minus here. Effectively, I can combine, right? And therefore, your x becomes, if I, just 1 second. And therefore, it's x equal to minus b by 2a. What happened here? Okay, so minus b by 2a plus or minus square root of b square minus 4ac whole upon 2a. So this b square minus 4ac is what is always at the center of attraction. So this is called the discriminant, right? So minus b plus or minus square root of d whole upon 2a. So a quadratic will always have two roots, except that in like when we are reading it at 8th grade or 9th grade, depending on d being positive or d being negative or d being less than 0 or equal to 0, we say it's 2 roots and 1 root and 0 roots. Technically, it always has 2 roots. In this case, it has 2 real roots. In this case, it has 2 roots which are repeated. 2 roots which are repeated. And in this case, it has 2 complex roots. That's the only difference. There are always 2 roots in a quadratic. Okay. So, and here also you can see that if the roots are minus b plus root d by 2a and minus b minus root d by 2a. So you can call one of them as alpha and one of them as beta. So let's say this is alpha and say this is beta. And therefore the sum of the roots alpha plus beta therefore becomes the root d and minus root d get cancelled, minus b by a, which is in confirmation with what we saw earlier also, right? Up above here, we saw the alpha plus beta, the sum of the roots was minus b by a. Okay, and similarly, the product of roots, if you have to do multiply alpha into beta here on the side. So minus b plus root d times minus b minus root d becomes minus b whole square minus root d whole square, okay, upon 4a square. So this is b square minus root d whole square is d, which is b square minus 4ac whole upon 4a square. So which is 4ac upon 4a square, which is c by a. So that's how you get the product of roots is c by a. So which is again in confirmation with what we saw here. This is the product c by a. This is the sum, this is the product. Okay, right. So the sum and product are quite important because very often we are not interested in the roots. We are only interested in the sum and the product. So we don't need to waste time. So typically you would have seen problems like this. So if I have x square minus 11x minus 3 equal to 0, right? And if alpha and beta are roots of this, then alpha and beta are roots of this, right? Then the question is, what is the find an equation whose roots are okay, I'll just make up something, right? Alpha by beta square and beta by alpha square, right? Something like this. Now, obviously, we are not able to guess two numbers which multiply to -3 and add to -11. And therefore, if you resort to solving it, you'll get like irrational numbers, very messy to deal with. Even as it is, they are that. And if you do alpha by beta square and beta by alpha square, it's going nowhere, right? So there's sum and product of roots. So the question is, find an equation whose roots are alpha by beta square and beta by alpha square. So you can use the sum and roots technique. So the sum of the roots in this case, the sum is minus b by a, which is 11. And the product of roots in this case is c by a, which is -3, since a is 1. Okay. Now, for the new equation that we are trying to discover, right? The new sum, I'll just call it S dash, right? The new sum is alpha by beta square plus beta by alpha square. I can do that as alpha square beta square times alpha cube plus beta cube. Okay. Now, I know, so this is my alpha plus beta, and this is my alpha beta, right? So I can write everything in terms of alpha plus beta and figure out, right? So I know alpha cube plus beta cube. So just to recap, alpha plus beta whole cube, a cube plus 3a square b plus 3ab square plus b cubed, right? So I can move the 3 alpha square beta and the other one to the other side. I can write it as alpha plus beta whole cube minus 3 times alpha beta I can take outside from these two, and alpha plus beta. So this just becomes alpha plus beta whole cubed minus 3 alpha beta into alpha plus beta whole upon alpha beta whole square. So the bottom line, I can write everything in terms of alpha plus beta and alpha beta, and the problem is done, right? I'm not going to numerically solve it, but we can do it. That's where, right? So we can find it, whatever this. Okay, I'm just randomly making some number. Let's say this comes to 38 something, right? It could be wrong, but I'm just saying 38. Similarly, let's say the product of roots is, in this case, it's very easy, right? Alpha by beta square times beta by alpha square just becomes 1 by alpha beta. So we know alpha beta is -3 or something, right? So therefore it's -1 by -3. And then I'll just say 38 by 9 something, right? And therefore we can finish off the problem. This is the new sum. This is the new product. Therefore, the new equation I'm seeking is x square minus the new sum of roots into x plus the new product of roots equal to 0. This is one of the forms we saw, right? Therefore, I can just complete the problem by saying, again, 38 by 9 is wrong. I'm just quickly illustrating, that's all. So something like this would be how you'll finish off. Without involving any irrational number, we have solved the problem completely, just by using sum of roots and product of roots. Okay, makes sense? All good so far. I'll just pause for a second. Let's see, Sid, you're okay? Dipra?
Yes, sir.
Yeah.
Arav?
Oh, yes, sir.
Okay, cool. Okay, so we have sum of roots. Okay, so in a way you can think of like a tripod type of thing, right? So you have a quadratic equation, ax square plus bx plus c equal to 0. So this is the equation. And then you have the roots alpha and beta. These are the roots. Okay, and this is the sum and the product of roots, right? S and P, right? Sum and the product of roots, which is minus b by a and c by a. Minus b by a and c by a, right? Now, all of them are connected, right? So depending on the situation, we should be able to adapt. Given an equation, we should be able to solve for the roots, either by factorization or by using minus b plus or minus that formula. Given the roots, we can find the equation also, right? How do I do this? If I know the roots as 3 and -7, my equation just becomes x minus 3 times x plus 7 equal to 0. That's it, right? I can put any number here in front, doesn't matter, because anyway you can divide by a. So effectively the a does not matter. So given the roots, I can find the equation. Given the equation, I can find the roots. Now we also saw that given the equation, I can find the sum of roots and product of roots very easily, right? So it's just literally minus b by a and c by a. So that's it. And given the sum and product of roots, I can find the equation as x square minus sum of roots times x plus product of roots equal to 0. Okay, and this is just minus b by a and c by a. Right, you're going to say the sum is so and so. And then the last bit in the puzzle is, given the roots, can you find the sum of roots and can you find the product of roots? It's like saying, do you know how to add? Do you know how to multiply? Right? Given the roots are 3 and -7, the sum of roots is -4. The product of roots is -21. Now, the only part which we cannot do is this guy, right? So this guy, I'm going to put a dotted line. Okay, so we can guess, right? For example, if the equation is x square minus 7x plus 10 equal to 0, I can guess, seeing the sum of roots is minus like 7, product of roots is 10, and therefore I can guess the numbers are 5 and 2. That's only guessing, but I won't always be able to do. If it's minus 7x plus 11 equal to 0, then I cannot guess, right? Because the roots are coming to be irrational numbers. Therefore, I'll have to take this route. So given this, so I'll have to first construct the equation. So let's say I'm given the sum and product of roots as 7 and 11. Then first I have to construct the equation, which is x square minus 7x plus 11 equal to 0. And then I'll have to solve it to find the roots. So that's minus b plus or minus root of b square minus 4ac whole upon 2a. And therefore, you'll just conclude saying it's 7 plus or minus root 5 upon 2. Okay, so you cannot directly go. So I can guess in some cases. I cannot guess in some other cases. Okay, but depending on the situation, you should be able to adapt moving from one block to another block efficiently.
Sir,
Okay.
one doubt.
Yes.
Sir, can we do it in x square minus 7x plus 11? So we can write it as x square minus 7x plus 10 equals -1 and then solve it.
Yeah, you can do it. But again, that's effectively same as completing the square. And so if I can write, he's saying you can write it like this. Okay, and then he'll say this is, but again, it brings to the same thing, right? How will you solve it? It brings x minus 5 times x minus 2
yes,
equal to -1.
equal to -1. So x minus 5 equals minus no.
No, that's the only problem. That's the problem, right? When the product
Okay.
is 0, you can say either this is 0 or this is 0.
Oh,
When the product is
yes.
anything but 0, you cannot do that. Ron, a good question. Thanks for bringing it up. But why is your video off, beta?
Okay, sir. Just
Okay.
turn it on.
Okay, does it make sense? But that's a good suggestion, but it'll fail. And let's say even
Okay.
it works, let's say, right? Let's say it works out to be something like 28 or 24, something. Then you'll have to find two numbers which are apart by 3, because this is x minus 5 and this is x minus 2, which multiplied to give 24, right? So which again is not feasible, right? 6 into 4, 8 into 3, 12 into 2, we try all of them. None of them are apart by 3. And why should they be apart by 3? Because I have x minus 5 and x minus 2. So again, it comes back to the guessing game. We fail in guessing, and therefore we have to resort to actual solving.
Okay, sir.
Okay,
Got it.
cool.
Okay.
Yeah. Okay, so back to the other forms. What was this? Okay, the Cartesian form is generally used only to just simply, any problem you start off with the Cartesian form. The only advantage there is you can see what the y-intercept is in plotting. If you were to plot the function, then my 0, c is got by just the Cartesian form, looking at the Cartesian form. Okay, now the sum and product of roots, we have illustrated why it's useful. The factorized form is useful to trace where it cuts the x-axis and y-axis, right? So if I have the factorized form, then I can say the quadratic, I know this is alpha, I know my alpha is -3, right? And my beta is +2. It helps me trace a function like this, right? So that's why this is. And the last one, the vertex form. So we say h, k is the vertex. Why do we say h, k is the vertex? Assume for now a is positive. Same logic holds good when a is negative. If a is positive, we are looking at this expression y equal to a times x minus h whole square plus k. The bare minimum that x minus h whole square can be is 0 because of the square, right? So even if x minus h is positive or negative, the quantity is going to be the lowest, again, when a is positive, right? Lowest when x equal to h. And that resulting quantity, the y value, would be a times 0 plus k. Therefore, the coordinates of the vertex becomes h, k. Right? So the coordinates of the vertex become h, k. Right? And that, what is h and what is k, also comes from this. So if I can just tweak it a little bit. So if I just say this is my y, okay, fine. Let's do this separately, right? So by again the same completing the square, I have y equal to a times x square plus b by ax plus c by a, right? By the same complete, but here a matters. I cannot divide by 0 because I'm not trying to solve. This is still an expression, so I have to retain the a. So again, let's quickly complete the square. So I'll write 2 times b by 2a times x plus b by 2a the whole square. Okay, and then plus c by a, and then I'll subtract the minus b by 2a the whole square on this side itself. Okay, so if I do this, then this becomes y equal to a times this entire unit is x plus b by 2a the whole square. Okay, and then I have a times c by a, which is just c, and then minus b square by 4a square. Okay, so I can write it as a times x minus b by 2a the whole square plus, I can write this as 4a square, and then sorry, I missed an a here. When I did b by 2a whole square, I multiplied by the a, so the same should carry here also. When I'm subtracting also, that will have an a, right? So this is minus a times that, right? So effectively it becomes b square by 4a. B square by 4a. So when I do that common denominator here, it becomes 4ac minus b square. So I can write this as a times x minus h whole square plus k, right? Plus k, where my coordinates of the vertex therefore become h equal to minus b by 2a. And it's no surprise because vertex is exactly halfway between the two roots. So it's the average of the two roots, right? So alpha and beta, the average of the two roots is minus b by 2a. And the sum of the two roots is minus b by a. So in this case, the vertex is this point, which is alpha plus beta by 2, which is minus b by 2a. Okay, and the y coordinate is 4ac minus b square. We recognize this better as b square minus 4ac are negative. Therefore, it's minus d by 4a. Right. So the vertex form helps in plotting where the vertex is. Right. So those are the four main forms you should be comfortable with. Now, the sum of fruits, product of fruits concept, we can, I think that's pretty much what I wanted to cover with quadratics. Is there anything else I missed? Of course, based on discriminant, you know all that, right? So if the discriminant is greater than 0, the function is going to cut at 2 points. And discriminant equal to 0, it'll still cut at 2 points, but the 2 points collide into 1 point, which is why it's a repeated root. And if d is less than 0, it's throughout above all of these cases where a is greater than 0. If a is less than 0, you can imagine similarly, it'll cut at 2 points or just graze through at 1 point or not cut at all, something like this, if a is less than 0. So all of this, you know. Okay, so I was saying the sum of fruits and product of fruits concept can be extended for cubic and quartic and any polynomial. So by that, what do I mean? So if I have y equal to ax cubed plus bx square plus cx plus d, okay, in fact, I'll say it's an equation, right? So suppose it's equal to 0. I can still find the sum and product of roots, but I can find something even more than just merely the sum and product of roots. So I would say you can find the sum product of roots. So what do you mean the sum product? So you can find something called S1, S2, and S3. Okay. So let the roots be alpha, beta, and gamma. There are 3 roots, right? So S1 stands for the sum of the product of the roots taken one at a time. So if you take one at a time, there's no product at all, right? So literally, it's just the sum. So alpha plus beta plus gamma, right? So it's the pure sum in this case. Okay, so hold on for just 1 second, then this will become obvious now. When you do sum S2, it means sum of product of roots taken 2 at a time, which means we have 3 combinations, right? Alpha beta plus beta gamma plus gamma alpha. So it's sum of product of roots taken 2 at a time. And then you can talk about sum of product of roots taken 3 at a time. So taking 3 at a time, there's only one way, which is alpha, beta, gamma. And this becomes the pure product. So the extreme ends are the pure sums and the pure products, right? And this, the same pattern continues here. This is minus b by a, and this is c by a, and this is minus d by a, right? You start with negative, and then you keep flipping minus and plus, minus and plus. And why is that? Because I can write this equation as the Uparwala equation. I can write it as a times x minus alpha times x minus beta times x minus gamma, right? And the other way of writing this is x cubed plus b by a times x square plus c by a times x plus d by a, right? Now, if I try to solve both of them, now what x cubed is coming from this x times this x times this x, therefore it's x cubed. Where is the x square coming from? X square comes from 2 of the x's multiplied by a constant, which in this case is minus gamma, or 2 of the x squares, 2 of the x's multiplied by minus beta. And similarly, with minus alpha multiplying this x and this x. So in other words, the x square term is got by minus alpha and minus beta and minus gamma. So which is why alpha plus beta plus gamma becomes this minus b by a. Does it make sense? Okay. Similarly, where is the x term coming from? If I have the x term, it's 1x multiplying 2 other constants. So this x could multiply minus beta and minus gamma, and symmetrically the other combinations, right? Therefore, you'll get alpha beta plus beta gamma plus gamma alpha. And note that now it's become plus because 2 negatives are multiplying. And similarly, the constant term is got by the 3 constants multiplying, which is alpha, beta, gamma, right? Which is why by comparison, you can say minus b by a is my sum of roots. And taken 2 at a time, the sum product of roots alpha, beta plus gamma alpha becomes c by a. And the product of roots alpha, beta, gamma is minus d by a by comparison this with this, right? And you can extend this logic for a 4th order also. So I'll just do a 4th order just so that it's clear. So the 4th order is, let's say, ax power 4 plus bx cubed plus cx square plus dx plus e. So there are 4 roots, alpha, beta, gamma, and delta, let's say, right? Then S1 will be the pure sum, which will just be only one way you can add. S2 will be some product taken 2 at a time. So there'll be how many of them? 4 choose 2, right? We haven't done combinations, permutations formally. We'll do it, but in 4, you can pick in 4 into 3 by 2 into 1, 6 ways, right? And you can see that alpha, let's finish alpha first. Alpha beta plus alpha gamma plus alpha delta. Then we'll move to beta, and beta has already been mapped with alpha, paired with alpha. So we'll go forward, beta gamma plus beta delta, and then we'll go gamma delta. So those are the 6 terms that we get by doing 4 choose 2. And then S3, which is some product taken 3 at a time. Taking 3 at a time is effectively leaving out 1. So I can leave out alpha, right? Or I can leave out beta, or I can leave out gamma, or I can leave out delta, right? So there are 4 terms, which is again 4 choose 3 is 4, right? And then the sum product S4 becomes the pure product, just like this is the pure sum. There's just one way in which you can combine all of them together as a product. So that becomes your 4th one. And therefore this will become, so this will become minus B by A. So this will become C by A. This will become minus D by A. And this will become E by A, alternating between plus and minus. Okay, so this is also useful, again, for situations where you're not interested in the roots, but only combinations of these roots, right? Some product of these roots. Okay. I think that's enough about quadratics and polynomials. Okay, so let's jump into basic permutation combination recap. So permutations. Any doubts so far in any of this? All of you okay? Okay. Okay. So permutations and combinations, right? So there are two different categories. So combinations is arranging. Sorry, combinations is choosing. Permutations is arranging. And you can choose and arrange. That combination is also there. Okay, if the problem might involve first choosing and then arranging, I would always like to separate out both. Keep the choosing game separate, keep the arranging game separate so that you don't mix up. Okay, so what is, again, many of you might have already done this. Let's say I have eight identical objects. In how many ways can I select 3, right? So let's say there are 8 identical objects. In how many ways can I select 3? So let me just ask Dipra. I have 8 identical chocolates. How many ways can I select 3 of them?
So 8C3.
No. Arav.
Does it with restrictions on like the order or with no restrictions?
No, I'm just choosing. I'm just choosing.
We want to be 8C3 only that.
It won't be 8.
It's not 8.
Because it's 8 identical objects. Let's say there are 8 identical chocolates. You want to pick 3 of them. There's only one way, right? Because it doesn't matter which 3. So you want to pick up 3 chocolates. You really don't care which 3 they are because all the 8 chocolates are looking identical to you. So there's only one way of selecting 3 from 8 identical objects. So the reason I mentioned this is sometimes they may trick you. Don't be fooled into always putting 8 choose 3. If there are 8 distinct objects, then it's 8 choose 3, right? So there are 8 distinct players and we have to select 3, which will represent our team. Then it's 8 choose 3. Okay, so that would be, does it make sense, guys? The subtle difference, Dipra or whoever else. Okay,
Yes.
so it's 8 into 7 into 6. And then, so, but when I say 8 into 7 into 6, I'm actually specifying an order, right? There are 8 people here. A, B, C, D, E, F, G, H. So I can call any one of them as the first spot. So I can, to form my team, I'm just looking at all my 8 players and say, okay, I need F. And then I look and then I see, okay, I need C. And then I look and then say I need H, right? But the ordering in which I chose them does not matter because ultimately my team is going to be only these 3 people. So which means I'm excess counting by the number of ways in which I can arrange F, C, and H. Therefore, it's 8 into 7 into 6 by 3 into 2 into 1, which for convenience, we can multiply by 5 factorial and 5 factorial so that you can write it conveniently as 8 factorial times 3 factorial times 5 factorial. Okay, therefore it just becomes this, right? Or more generally, if I have n choose r, for writing it conveniently, it becomes n factorial upon r factorial times n minus r factorial. Okay, and then of course 8 choose 3 is same as 8 choose 5. If I have to form a team of 5, or rather in the extreme case, let's say I have 100 people, I have to form a team of 95, right? Just imagine, I'm not going to select my best 99. I'm effectively going to only select my worst 5 and say you are ruled out, the rest of you are in. But the problem of choosing is exactly same as the problem of elimination. If I choose 5 which are bad, automatically I'm choosing the 95 which are good. So the number of ways in which you can form those groupings is still the same. So n choose r, and you can see that from symmetry in this expression as well, right? If I just replace it with r with n minus r, the denominator becomes n minus r factorial times n minus r, which is back to r. So n choose r is same as n choose n minus r. And then if I have 10 choose 0, right? How many ways can I select 0 objects out of 10 different objects? Only one way. The act of not choosing anything is one way, right? And likewise, how many ways can I select 10 out of 10? Only one way. I literally have to pick up everything. So n choose 0 is just n choose n, which is 1. And then similarly, n choose 1 be n choose n minus 1, which will be n itself. Of 10 people, how many ways can I select 1? Any kindergarten will tell it's 10 ways. How many ways can I select 9? I just have to pick up who's not selected, right? Effectively the same 10 ways, right? So n choose 1 is same as n choose n minus 1, which is n. Okay. So these are the main extreme ends, right? So when we write an, in fact, we'll do binomial expansion right after this, and this will be clear, right? Those are extreme ends. And then the other thing I wanted to say is, if I have n choose r plus n choose r minus 1, that is same as n plus 1 choose r. N plus 1 choose r. Yeah, okay, all right. I'll give an example. It's always easy to with an example, right? So what I'm saying here is, if I have 16, let's say n is, I'll just put n equal to 15, right? So 16 choose 11, and I'll tell you why I'm choosing n plus 1 as 16 or something, right? Let me rewrite it in a better way. Sorry, I'll say n choose r is same as n minus 1 choose r minus 1 plus n minus 1 choose r. Okay, so let me give an example with n equal to 16 and r equal to 11, right? So what is this 16? This is the squad. So you have a, let's say cricket, you have a squad of 16 that's representing India. And finally, only 11 will be in the playing 11, right? So from a squad of 16, I'll have to select 11. So 16 choose 11, I'm saying another way to look at 16 choose 11 is 15 choose 10 plus 15 choose 11. So why is this? So if I have to select 11 from 16, okay, let's say I'm looking at all the 16 players and randomly I look at one player X, right? My thought process would be, I definitely want this guy, or I definitely don't want this guy, right? If I definitely want this guy, then my problem reduces to, from the remaining 15, I'll have to only select 10. Correct? This guy X is definitely in, let's say, right? This guy X is definitely in, then my problem reduces to, from the remaining 15, I have to pick up 10. On the other hand, if I look at X and say this guy is hopeless, I definitely don't want him, right? Then my problem reduces to, from the remaining 15, I'll have to select 11. So it's only going to be one of these two cases anyway, right? Therefore, you get this expression, right? And then this is what you'll effectively see in your Pascal's triangle as well, right? In your Pascal's triangle, how do you build your Pascal's triangle? It's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6. All of you would have seen Pascal's triangle. I don't need to talk about it. So 1, 5, 10, 10, 5, 1, right? So all of these are your choosing, right? So this is 5 choose 1, 5 choose 2, 5 choose 3, and so on. So in this example, let's say I'll take these 3 and illustrate. So here I'm just saying this object is 5 choose 3. So 5 choose 3 is nothing but 4 choose 2 plus 4 choose 3. This is 4 choose 2, this is 4 choose 3. This is 4 choose 2. This is 4 choose 3. This is 5 choose 3. So you can see that happen in the past, which is why you keep adding up and putting the number, the sum in the middle. Okay. All right. So given, and then, okay. So permutation is very easy, right? So given R objects are there, you can arrange them in R factorial base. So there's R objects, and you can, let's say R is 4, you can put them in 4 factorial base. And if things are arranged in a circle, then it's R minus 1 factorial base. So by that, you have to be careful. What do you mean by the circle? So in a circle, relatively speaking, it's R minus 1 factorial. So let's say there are 8 people sitting in a circle. So 1, 2, 3, 4, 5, 6, 7, 8. Let's say relatively they are sitting in a circle, right? So if there is a, for example, if there's a door here, right? Then it's not really a circle, because I have some association saying this guy is closest to the door. It's effectively like how they are sitting in a straight line only. But just imagine they are rotating in space somewhere, right? Then if I'm looking at the sky and seeing, then I won't be able to tell any difference between how they're relatively placed. So in that way, sorry, I'm not expressing myself clearly. All I want to say is, here it's 7 factorial base, here it's 8 factorial. Just because it's a circle, don't immediately put the number of ways of arranging them as R minus 1 factorial. It depends on the context, right? If I have a door here, then this guy gets special attention because this guy is closest to the door. If I effectively same as lining up in a line where the starting position is something. But if there's no starting position at all, if they are all rotating randomly, just imagine it's a table which is continuously rotating in the sky, then you won't be able to tell a difference. You have to start with somewhere, and relative to that person, you have to arrange the other 7 people. Therefore, it's 7 factorial base of arrangement. So the takeaway from here is, just because you have a circle problem, don't blindly put as R minus 1 factorial. Understand the context. Okay, so it's R minus 1 factorial relatively. So the word relative is important. Okay. Okay, so given we are doing permutation combination, the next thing is binomial expansion, right? So if I have a plus b whole power n, right? So that's nothing but a plus b times a plus b times a plus b, so on n times. So it's very related to our choosing business. Why? Because how many ways can I have a power n? Every a must multiply every other a here. So there's literally only one path to reaching a power n, which is why the coefficient of a power n is just 1. And then if I have, the next one is a over n minus 1 times b power 1. So similar to that sum product of roots that we were doing, right? So we'll have to pass through n minus 1 a's and 1 b. That 1 b could come from any one of these guys. This might be the b in the first multiplication. In the second multiplication, it might be this b multiplying by the rest of the a's. Like that, the b can vary. All of those products are going to give the same a power n minus 1 times b power 1. And therefore, there are n ways in which you can pick which is the particular factor where b is coming from. So in other words, it's n choose 1. Of the n, you're picking which is where the b comes from. And then extending it, you can have likewise, which are the 2 places where b square is going to come from. And therefore, the coefficient of this is n choose 2. And so on. So this is n choose 0 because you don't want any b. So there are 0 places from which you're picking b from. So all a's, n choose 0. And then all the way till n choose n minus 1. The penultimate term would be that a power 1, b power n minus 1. And the last term would just be n choose n, a power 0, b power n. Okay. So in other words, I can write a general term here as n choose r. Okay. A power n minus r, p power r. This is a general term. And I can just do a summation in front of it. So I can say a plus b whole power n is just summation of this. As r being the running variable, r goes from 0 to r goes to n. Sometimes you don't put r equal to in the numerator, in the above. It's understood, right? We're talking about the same running variable as we are talking here, right? So r goes from 0 to n. So this becomes the expansion for a plus b whole power n. And which is why you see a symmetry in, right? So this is n choose 0 matches with n choose n. Both are 1. n choose 1 is same as n choose n minus 1, which are both n, and so on. N into n minus 1 by 2. And then similarly, the penultimate term, the term before this would be n into n minus 1 by 2, and so on, which is something you see in the Pascal's triangle as well. Right? So 1, 4, 6, 4, 1. When we did a plus 5, a plus b whole power 5, these two matched, and this is the center term. So a plus b whole power n will have n plus 1 terms, just like a plus b whole square had 2 plus 1 terms. Yeah.
Sir, can you explain this again?
Which part, please?
So from the summation.
Okay. Do you agree that a general term is this? Right? If I pick any general term, right? So in this case, r is 2. So I'm replacing r with 2, right? So there are r locations from which I'll have to collect my b's, and n minus r locations from which I have to collect my a's. So therefore, of the n places, so let's say n is 10. So a plus b power 10. I'm looking at specifically the coefficient of a power 6, b power 4. Then what will I do? I'll say which 4 places I'll have to select my b from, right? And the remaining places will be my a's. So the coefficient of that would be 10 choose 4.
Okay.
And then when I expand, obviously I'll have to run my r all the way from 0 to n. As I said, right? You can pick 0 b's or 1 b or 2 b all the way till n b's. And therefore, there are n plus 1 terms in this expansion of a plus b whole power n.
Okay.
Okay, makes sense.
Yeah.
Okay, now, and you saw the symmetry also. So the Pascal's triangle, you saw the symmetry, right? 1, 2, 1, 1, 3, 3, 1. This is a plus b whole cube. This is a plus b whole power. What did I say? A plus b whole power 5. Maybe my mistake I did. It's a plus b whole power 4. And then the next one would be power 5. Okay, so this is a plus b whole power 5, coefficients of those, right? Now, it's clear that the coefficients are symmetric from the left hand and the right hand. The other important thing is there are a couple of special cases that we can derive from the Pascal's triangle here. If I sum all of these numbers, I get 1 here, I get 2 here, I get 4 here, I get 8 here, 1 plus 3 plus 3 plus 1. Here I get 16, here I get 32. So you can see the pattern here that the sum of the coefficients of a plus b whole power n is 2 power n. And why does that happen? That happens because if I put a special case, saying a equal to 1 and b is also equal to 1, then the left hand side just becomes 1 plus 1 whole power n, which is 2 power n. And the right hand side becomes the sum where each term is just n choose r, 1 power n minus r, and 1 power r. So this is all 1, 1, 1. So in other words, the sum of the binomial coefficients is just n choose r, right? Which is 2 power n. So in other words, n choose 0 plus n choose 1 all the way till n choose n, which I add up, which is what the sum is 2 power n. Okay. And also the other special case I can do is by putting a equal to 1 and b equal to minus 1. So if I do that, then the left hand side becomes 1 minus 1 power 0. So it's 1 plus minus 1 whole power n, I'm sorry, which is 0. And the right hand side becomes again n choose r. One of them will be 1 power something, which will always be 1. The other one will be minus 1 power something, which will alternate between plus and minus. So this summation would be, I can write this as summation of n choose r times minus 1 power r. Right? This will become minus 1 power r. The 1 power n minus r is anyway 1. So in other words, if I alternate, if I do 1 minus 5, plus 10 minus 10, plus 5 minus 1, all of those coefficients will add up to 0, right? And you can see this in this case because the minus 5 cancels off the plus 5, plus 10 cancels off minus 10. But more interestingly, it happens even in a case where it's not perfect cancellation. You have 1 minus 4, plus 6 minus 4, plus 1. The 6, 1, and 1 cancel off with the minus 4 and the minus 4. So either way, depending on n is odd or even, which is why we see these expansions, right? When you have a minus b whole power 4, it's exactly this. A minus b whole power 4 is a power 4 minus 4a cube b plus 6a square b square minus 4ab cube plus b power 4. You can see the coefficients adding up to 0. Because if I put a equal to 1 and b equal to 1, or rather, if I can treat it as a plus minus b, either way, right? You get the idea that the sum of the coefficients will be 0. Okay. So binomial, that's pretty much what I wanted to cover. And you should be able to figure out, this is something you would have done in school stuff itself. So if I have some random expression like x cubed plus, or rather x cubed minus 2 by x whole power 100, let's say, right? And then you should be able to find any particular coefficient, or can find the coefficient of, let's say, x power 78, something like this. X power, will 78 work? Let me just see. Okay, fine. We'll find a coefficient of x power. I'm just struggling to wake up an example. Let's say x power 220, something like this, right? Then we'll just say any expansion of any term in this case would be x power 3 power 100 minus r times minus 2 by x power r, and then this is 100 choose r, right? So starting from x power 300, if r is equal to 0, this is 300, right? So all the way till x power minus 100. The last term would end in x power minus 100. Now we can determine the power of x. The power of x is 3 times 100 minus r plus your minus r here. So 300 minus 3r minus r, right? That's the coefficient of x, the power of x that you're seeking. You want this to be 220, let's say. And then you can back solve. You can just say 80 equal to 4r. And therefore, I'll say r equal to 20. So which means the 21st term, or if you're counting from 0th term, first term, second term, the 20th term in such a case. So the term that we are seeking would be 100 choose 20 times x power 3 power 80 times minus 2 by x power r is 20, right? 20. And you can just check it. 3 times 80 is 240. X times 20 is 20 with a negative sign. Therefore, 240 minus 20 is 220. Therefore, you have your x power 2. And therefore, finish the question. The coefficient would be 100 choose 20 times the minus 2 power 20. That should not be ignored, right? So this minus 2 power 20 is anyway 2 power 20. So I can just put plus. And then this is the coefficient that we are seeking. Okay, all right. So, and then in permutation combination, I just want to do one or two other distribution type of problems. So typically you have the distribution of identical chocolates, let's say. Okay, so let's say you have, let's say a teacher has 4 students. So 4 students, and then he has to distribute, let's say, 12 chocolates. Okay, 12 chocolates. Now, and let's say different possibilities in framing the question. Let's say 12 identical chocolates in this case. 12 identical chocolates, and then each student can get any number of chocolates, 0 or more. For example, let's say the 4 students are A, B, C, D. The teacher might be pretty biased and might not like P at all. He might end up giving 3 chocolates here, and he really likes C, and then a total of 12, right? So fine, I'll just make it 8 chocolates here, and then 1 chocolate here. So this could be one example distribution, or could be a very fair teacher and give 3, 3, 3, 3. This is another example. Like this, there are multiple ways in which you can distribute. So the question is, how many ways can you distribute? The standard way of tackling this question is using, there are different words people use, bars and dots or something like, let's say if I lay out, well, I'll just draw a picture. There are 12 of them. So these are the identical looking chocolates. As far as the teacher is concerned, A, B, C, D are waiting, right? All he has to do is he has to create 3 partitions, right? Or rather, he has to create 4 partitions for which he needs 3 sticks. So let's say he puts the first stick here, first stick here, okay, and the second stick here, and the third stick here. Third stick here. Okay, fine. Right? That means A knows automatically to come and grab this, B knows to come and grab this, C knows to come and grab this, and D knows to come and grab this. right? That's one way in which you can distribute. Another way you can distribute can be the one where I said was a little unfair, where B got 0, so and A got 3, right? So the first stick is here, A got 3. Second stick was here itself, which means B ended up getting what was there between the two sticks, right? Which is literally, so B ended up getting this gap, which has 0 chocolates in it. And I think C was whatever, all of them in between, and then D got 1. So there are a couple of illustrations where I can put the bars next to each other also. So the problem reduces to how many ways can I arrange, how many ways can I just treat these as A's and B's, right? So there are 12 A's, right? And there are 3. Why 3? Because it's 4 minus 1 B's, right? There are 4 students, and therefore there's only 3 doors. You need to make 4 partitions. So how many, now the question reduces to how many 15-letter words can I make using 12 A's and 3 B's? So the problem reduces to how many 15-letter words can I make using 12 A's and 3 B's? And that's very easy, right? I just have to select which are the 3 spots in which my B can fall. So it's 15, choose 3. In other words, how did I get this 15? It's 12 plus 4 minus 1. Choose 4 minus 1. Or you can choose the 12 A's. That's also fine. 15 choose 3, same as 15 choose 12, right? Ultimately, it's same thing, right? So you have 12 kids, and then, 12 chocolates, 4 kids. Therefore, we need 4 minus 1 doors to form 4 partitions. And then you just have to figure out where to put those doors. So among the 15-letter word comprised of 12 A's and 3 B's, where do you put the B's? So it's 15 choose 3. Does it make sense? All of you okay on this? Rahul, you're okay with this? Okay.
Yes.
Okay. Now, of course, if the question is each student must at least get 1 chocolate, right? You cannot let anyone go empty-handed. Then we can reduce the problem. We'll say there are 12 chocolates. First, give all of them 1, 1, 1, 1. So at least they'll be satisfied. Now the problem reduces. Now there are 8 chocolates, and then back to the original question. Now I can afford to give 0, right? So the back to original question, after giving 1, 1, 1, 1, it's back to the original question. Therefore, my answer would be this. Whatever, 8 choose. How much is this? 11 choose 3 base. I've given all of them 1. Now, this is in the case where the, sorry, someone chatting me here in between. Okay, I don't know. Aditya, you wrote to everyone, I guess, instead of just me. Okay. Now, the other question I had was, would be if the chocolates are non-identical chocolates. So non-identical chocolates. The chocolates are non-identical. Then how do we distribute? Again, there are 12 chocolates, and anyone can get anything, right? There are A, B, C, and D, right? So you go to each chocolate. So this chocolate looks like this, 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 something, right? Each of these chocolates has different shapes. You go to each chocolate and ask, right? I'll just draw another one, right? Something. Okay, so I just want to show that it's a different number than this, right? A, B, C, D. You go to each chocolate and ask, who do you want to go to? Do you want to go to A or B? Or this chocolate says I want to go to A. This chocolate says I want to go to D. This chocolate says I also want to go to T. So you get 4 possible responses from each chocolate, and you scan through all the 12 chocolates. Therefore, it's 4 into 4 into 4, so on 12 times. So it's 4 power 12 ways in which you can distribute. Okay. And then here it becomes a little tricky if each person has to be granted at least 1 chocolate. Then it becomes difficult because I cannot randomly pick and say, give each of them 1, because which one of the 12 different chocolates are you going to give? So obviously it's very clumsy, but of course you can have an easier problem with that. Let's say you have only 5 chocolates and 3 kids, then it's still maneuverable and you can still do it, although the approach will be slightly different. Okay, so you've covered the essence of quadratics, polynomials, binomial expansion, permutation, combination, and then last week we did quite a bit of algebra. Okay, so maybe another 1 or maybe 2 more sessions I'll need to cover the basics. So we haven't even started geometry yet. So geometry, trigonometry, complex numbers, all of these will collectively maybe take 1.5 or 2 sessions. Let's see, I don't want to rush, but I'll be somewhat at this space only, and then we'll do topical questions. Okay, so let's end the class here. See you guys.
Bye, sir. Thank you.